Hi, I'm Stefan and I work with Jason Anderson. As engineers, we often need to do computations. No matter what discipline we're in, we have to calculate things. And there are two main ways we can do that. A very familiar one is to write software. We all know about software running on our laptops, on our processors. Software is written in a programming language, like C, for example. But equivalently, we can also design custom digital circuits to do all the same computations. This isn't as familiar, but your phone's a good example of this. Your phone has a lot of custom circuits like these ones, which each do one thing and one thing very well, very low power and very efficiently. So as engineers, we have this design choice. We can write software, which is easy. Every first-year engineer learns how to write code. But writing code doesn't have the same power and performance benefits as designing custom circuits, which unfortunately are more difficult to design. One solution, however, is something called high-level synthesis. And what high-level synthesis lets us do is design circuits using a high-level software language. So for example, an engineer can write a C program, and a high-level synthesis compiler will automatically convert this to an equivalent digital circuit. So this is great because now we get the benefits of programmability and performance. A problem, however, is that currently high-level synthesis tools don't automatically generate circuits that are of equivalent quality to what an expert engineer would make. So there's currently a gap in quality. And there's a lot of research being done right now to improve the quality of these circuits. Specifically, my thesis focuses on improving the circuit speed. So let's start with a quick review of digital circuits. Let's say you go to Future Shop, you buy a 1 gigahertz processor. What does that mean? It means that every computation that this circuit does is broken up into 1 nanosecond intervals. So across time we're doing lots of computations, but each is scheduled in a 1 nanosecond window. So for example, let's say we have this circuit. It calculates A plus B. These symbols at the inputs and outputs are called registers, and they just store the computation after every step or every clock cycle. Okay, so in 1 nanosecond we can calculate A plus B. We can also do other things in parallel. The next nanosecond we can do some other computation. The third one we can do something else and combine them all at the end. Okay, so we've calculated this expression. Let's say instead we have a slightly different circuit though. Let's say instead of doing E times F, we did E divided by F. So it turns out that in these circuits, some operators have more delay than others. For this example, let's just say that dividers take 2 nanoseconds to complete. Well, this is unfortunate because now this is going to delay the entire first step and make it last 2 nanoseconds. But actually, a constraint of digital circuits is that each one of these steps has the same duration because the circuit runs on something called a clock. So what's going to end up happening is that every one of these steps is going to be delayed to 2 nanoseconds. Well, that's really unfortunate because every other instruction can finish in exactly 1 nanosecond, but this one divider, sort of like this one straggler, is slower than everyone else, but it's delaying the entire circuit to 2 nanoseconds. If we look closer though, what we notice is that actually this divider isn't required until 2 steps later. So what we can actually do is we can extend its deadline and allow it to finish in step 3. This is great because now the divider can take its 2 nanoseconds to finish. And we've created what's called a multi-cycle path, which means that now this divider can take 2 cycles to finish instead of 1. So this divider can still take its 2 nanoseconds, but it's not going to slow down the rest of the circuit in the process. So that was the first key idea I wanted to introduce, this idea of a multi-cycle path. It turns out that there's actually another way we can do the same thing. So we introduced this idea of multi-cycle paths or extending the deadline so that we can take a big computation and allow it to complete in more time. Another way of doing the same thing is something called pipelining. What we can do is we can take a long computation like this and we can break it up into many smaller chunks. So each of these smaller chunks still takes 1 nanosecond to complete, or 1 clock cycle, whatever it is, but we've broken it up. And it turns out this is actually the exact opposite of the first topic I introduced, multi-cycle paths, because if you take a pipeline path like this, so a long computation that's broken up, we can actually de-pipeline it and then add a multi-cycle path. So it's just 2 ways of doing the same thing, either breaking it up into smaller steps or having 1 long step but extending the deadline. It turns out that the first method I talked about, multi-cycle paths, actually have a lot of benefits compared to pipelining. I won't go through all of them, but essentially they can make your circuit a lot faster. However, there's a huge disadvantage associated with multi-cycle paths, and that's that you can't introduce new data into your circuit every cycle or every step. And the reason is that each of these paths take multiple steps to complete. It turns out that for a lot of circuits, this is a really big disadvantage. So we actually don't always use multi-cycle paths. But in high-level synthesis, when we're automatically generating these circuits from software specification, it actually turns out that it's not a big problem to not be able to have new data every step. So we actually can take advantage of a lot of these benefits of multi-cycle paths. So that was the second key idea I wanted to talk about, this idea of de-pipelining a circuit and adding multi-cycle paths. And I'll give an example to make that more clear. So let's say that we have this circuit, okay? And every step we do some computation. The first thing we can do is then we can de-pipeline this. So we take a pipelined circuit which has many steps, depipeline it and instead replace that with a multi-cycle path. Okay, so we've extended the deadline of this computation to be 4 in this case. It turns out that if we do this across a suite of 13 benchmark circuits, we get speedups. So here I have 13 benchmarks on the x-axis, and on the y-axis I have the circuit speed, or the clock frequency. And we see that in many cases the circuits get faster just by doing this depipelining. Some circuits still get slower because of one bug that I'm currently fixing, but in general we see that there are big speedups because of this change. The red is without any changes, and the green is with the change to add multi-cycle paths. Okay, but we can do better. Remember that high-level synthesis is great because it lets us design circuits using a high-level language. But unfortunately, the software doesn't perfectly map into hardware, so we don't always get perfect implementations of these circuits. Okay, but that's being pessimistic. We can also focus on the upside of starting from software. And one advantage of starting from software is that we get access to a lot of software profiling tools that can make our lives easier. So this is an example of a software program. It doesn't matter what it does. All that matters is that there's some computation, let's call it computation A, that happens first. Then we have a branch. If one thing is true, we're going to do computation B. If something else is true, we're going to do computation C. And at the end, we'll end with D. Okay. We can run something called a profiling tool on this software. And what it might tell us is that, okay, branch B ran about 3% of the time, and branch C ran about 97% of the time. If we then take the software program and convert it into a circuit, what this means then is that whatever's calculated in part B of the circuit will be used about 3% of the time, and what's calculated in part C will be used about 97% of the time. Okay, now let's think back to that example I showed at the beginning with that divider. It was just an example. It didn't have to be a divider, but in that case, that divider was sort of the slowest part of our circuit, slowing everything else down. It would be really unfortunate if that divider was in part B of our circuit, because part B is barely even used. But if the slowest part, if the critical path of the circuit is in part B, it's still going to slow down the rest of the circuit. So how did we fix that problem? In that example, we fixed it just by extending the deadline of the divider, saying to the divider, okay, you can take an extra step to complete so that you're not the critical path. In general, though, we can't always extend the deadline. If we did that for everything, our circuit would take many more steps to complete. But it turns out that if we actually extend the deadline of everything in B, it won't really make that much of a difference to the overall circuit, because B is barely even used. But by doing that, we can ensure that the critical path, or the slowest part of our circuit, will not be in B. So it's kind of a complicated point to explain, but let me give an example to make it clear. That was the third key point I wanted to introduce, this idea of software profiling. So let's put them all together. So let's say we have this part of our circuit, this path in our circuit. And let's say that the critical path of our circuit is right here, and it's 94 megahertz. Okay, we want to make this faster. So the first thing we can do is our trick to depipeline our circuit and add a multi-cycle path. Let's say if we do this, our circuit speeds up to 100 megahertz. Okay, that's great, but we can do better. Let's say that we then run a profiler on the software that generated this circuit and see that it executes about 3% of the time. What that means then is that we can then extend the deadline of this part of the circuit. Let's say it took 4 cycles to complete. We can let it take 5. Doing this will extend the overall number of steps in our circuit, but because it only runs about 3% of the time, that's not a big deal. However, that would increase the speed of this part of the circuit from 100 megahertz to 125. And if this was a critical path for our entire circuit, the whole circuit would speed up. So I'm still working on implementing this, but it really should give promising results. And I'm excited to see how that turns out. To summarize, high-level synthesis is great because it lets us design circuits so much more easily. And using software profiling with multi-cycle paths is a really promising way to get better and higher speed circuits. Thank you.